we will go on with the agenda, and our next speaker is Ramses Valvekens from the ASICs company. And Mr. Valvekens will speak about platform-independent and scalable real-time embedded neural network interface. So, the stage is yours.
Thank you. Welcome also on my behalf. Thank you for the kind introduction. So I'm Ramses Valvekens from a company called easics, and we're going to talk about neural network inference embedded on FPGA, on ASIC, and how we can do that in a platform-independent and scalable way, and also do it very close to the optimum performance that you need for your application. So first of all, I will briefly introduce my company, easics. I will also introduce our embedded neural network inference technology called nearBAI. And then, of course, we will go into the details of how do we do that at platform independence, how do we make it scalable, and so on. And then we go to the conclusions. First of all, about easics. easics is a company based in Leuven, Belgium. Exists for 30 years, founded in 1991. We are an independent company now. What do we do? Two things, products and services. The products you can see over here. Prime product is clearly nearBAI, product for doing neural network inference on FPGA or on ASIC. And then we have as well some TCP/IP offload engines, hardware engines to do the full TCP/IP stack in hardware so as to get the lowest latency you can achieve. The business model for those products is clearly semiconductor IP licensing. So it's IP cores that you can implement on your FPGA, on your ASIC application, or we can do it for you. Of course, associated with a couple of development tools to assist that process. Second part of the business, as I said, services. So it's a design service business. So what we do is we do custom FPGA design and custom digital ASIC design. Can be a full chip, can be a macro, for example, a digital macro inside of an image sensor. Besides that, we're also involved in architecture. How are we going to implement that? And in fact, do entire design conceptualization, as well as even product ideation, assist the customer in really getting to that optimal mix of performance versus cost. Just to show you some of our experience, a lot of that is in signal processing, is in image processing. Some examples, it's really oftentimes about implementing digital pipelines of digital signal processing algorithms, a lot in imaging, in FPGA, in ASIC, inside image sensors, inside cameras and so on. There's a bit of embedded software development as well. And oftentimes, of course, it's mapping algorithms created in software languages on hardware, on digital hardware pipelines. Just some examples here of some neural networks that we are doing and that we did. Hand gesture recognition is in there. There is combining image and LiDAR data to do tracking of cars. We have even networks to detect keywords in audio, so it's not only about vision. And we can, of course, also do sensor fusion, where we are combining several sensors. We're just showing some of the sensors, some of the customers here. That goes all the way from companies like Cochlear, which is a company that is a world leader in doing cochlear hearing implants, very small medical equipment, all the way over some image sensor manufacturers, there's many more actually, and also all the way up to ESA, European Space Agency, doing digital processing inside of satellites, for example, to do Earth observation. In what markets are we active? That's mostly in the healthcare sector, in Industry 4.0, in consumer electronics, as well as in a couple of other markets, including automotive and space, as I mentioned. Okay, introducing nearBAI. What is it? nearBAI is, as the name says it, nearby, close by. It's basically AI in the sense of neural networks and neural networks inference, so doing the actual pattern recognition close to the sensors, typically in applications with low latency. A couple of features there. What is quite interesting, very interesting actually, is that nearBAI, as a technology, as an IP core, as a hardware IP core, is not tied to one particular FPGA family or FPGA vendor. So we're really platform independent, and we can target it to the Xilinx FPGAs, to the Intel Altera FPGAs. For example, also we're starting to support Phoenix, a new and upcoming FPGA vendor, but especially also to ASIC. We can map it to ASIC as well. And besides the FPGAs, we of course also do the FPGA SOMs, the system on modules, that allow you, of course, to rapidly prototype and even go into small volume production. And FPGA SOM is that small board that contains not only the FPGA, but typically also the associated memories and a couple of other auxiliary components that you always need. And that's, of course, much more handy. So it's compact, it's reliable, it's scalable, and we can also support very long product life cycles in the sense that we are not tied to a particular FPGA family, and that we can also support future generations out of your same development, of your same trained network, etc., etc. So in the end, it's maximizing your return on investment for any AI development, any embedded AI development that you are doing. So of course, we go for the optimal mix of performance that you need for your application. We are ultra low in latency, or we can go ultra low. We are also, of course, doing non-variable latency. One of the nice things about FPGA and ASIC, oftentimes, again, human-in-the-loop applications, VR, AR, and so on. Of course, low power is also oftentimes in the mix, and we tend to strive to find that optimum again for your application, and that is what our nearBAI allows you to do. I will show you in a minute. So this is basically the overview, our embedded AI cookbook, if you will, when you are using the nearBAI technology. Essentially, we decouple the mapping of the neural inference engine on your hardware, on your FPGA, on your ASIC. We decouple that from creating, designing the network, or just merely selecting it if it's one of the existing neural networks, selecting it, labeling your data, training the system with your data, using a blind data set, of course, to validate the performance of your network in terms of performance, in terms of the accuracy that is at that point. We really decouple that from the embedded story. This is very important. So how do we do that? Well, you can use any framework that you like. It can be any of the open source frameworks like Keras, TensorFlow, and so on, or a commercial package if you like. And as a starting point for using nearBAI, we use the ONNX file format, which is, of course, a file that contains not only the network topology with all the calculations, but also the weights, the trained weights, the coefficients, all in that model. So once you have that, we load, or you load that into the easics nearBAI development tools. It will parse that file, and it will use that iteratively with your help, with our help. We can help as well, of course, to find again that optimum, to generate that hardware core, and also to generate some microcode that runs on that hardware. So the end result at the right hand is indeed that nearBAI engine tuned again to your application that you map on an FPGA of your choice or on an ASIC of your choice, and that takes into account hardware constraints that are not taken into account in the traditional frameworks that you use to train and to validate your model, but of course are critically important in a hardware mapping. Just some examples to show you where we apply that. I mentioned already typically low latency applications where that really matters. Can still be human in the loop, or it can eventually become autonomous applications. First one here is healthcare, endoscopy. In this case, it's actually colonoscopy, doing inspecting the colon for polyps, for potentially colon cancer. So a specialist doctor is looking at these images in real time. It's actually a lot of data. And the AI is kind of as a digital assistant looking at it as well. And if it sees something suspicious, it will actually notify the surgeon, hey, have you seen it? Look again, and so on. It's a kind of a nice thing to avoid potential errors. Second application, I think is also well known, is using LiDARs in cars. LiDARs, of course, are much more robust than regular cameras through all the different conditions of the weather to look at other vehicles. And in the first application, to do things like collision avoidance and some driver assistance, and eventually, going, but it's going to take a while, of course, to the self-driving cars. So we're using neural networks here, directly using the LiDAR data to detect the cars. A third one that we're showing here is in space, kind of a really different one. So this is AI, neural network inference applied in satellites. It's actually starting to happen for doing Earth observation. In this case, it is showing, it is detecting some oil spills that may happen, and that the system wants to detect. The use case is clearly a reduction of the data and not having to send all these images down to the Earth, but really the summary of what is important. Just quickly here, we are of course not dependent on any sensor. There's many sensor modalities that we can use. Image sensors of all kinds, including X-rays, LiDARs, and so on and so forth. But of course also audio and other systems and sensor fusion. It just depends on the network, and we can run it. This is an overview of how such a hardware core, how nearby, how that engine, how it looks like. I would say no surprises here. It's a set of systolic arrays doing the convolutions. This is the heavy weight lifting, let's say, of all the calculations with lots of multiplications going on. There's the accumulation to, in the end, form the convolutions. We have a post-processor that is doing all the other things like the bias, like the activation functions, maybe with a nonlinear function like tangents hyperbolicus and things like that. And in the end, what it does, it is shifting in column by column in that array your image data. It also needs to load the weights, the trained coefficients from your network. And then it outputs, of course, the results. What is key here is to be computationally efficient. So we need to keep the hardware as busy as possible and not have too much idle time. And we have to configure the system so as to achieve that. On top, you see an Axie4 DMA controller that is going towards memory. And typically, the coefficients, they are quite large. When you look at the total size, it can be hundreds of thousands to even tens of millions of coefficients times a width of maybe 16-bit. Or 8-bit, depending on, but it's typically external, so that's connected. We do have support with direct memory access as well, with shared memory for adding a processor that could assist in supporting some additional operations, and that is very interesting that we can do it, but I want to stress that the solution as such doesn't need a processor. So the full inference is running on the hardware, and the software is there as a bonus. I'm now showing you the flow. With nearBAI, the first step, again, as I said, is training the network, and you use the software framework of your choice, like Keras, like PyTorch, TensorFlow, and so on, or a commercial tool. And in the end, you write out that ONNX with your trained model, with, of course, the network topology, as well as your weights, your coefficients. And that is really the starting point for nearBAI. And it's really important that we really make this decoupling and we are independent of that
you can use whatever you like. Typically, those ONNX files are written out in floating point, 32-bit, and we will do the quantization inside of the nearBAI, even though you could also do a quantization of the weights of the coefficients up front, and we can support that as well. When you then look at the implementation flow, there is 2 steps, and one is really interesting. We start by, again, using that ONNX, but also your hardware constraints. And with the estimator tool, we can very rapidly give you estimates of the performance. What are we doing in terms of latency, in terms of frame rates, in terms of other parameters, even power we can deduce from that, size of the FPGA, and it's typically an iterative thing. And this is key, that you can make these iterations very quickly, and the tool runs within a second and gives fairly, well, really accurate representations of what you get, and this allows you to fine-tune your requirement to make something realistic in an FPGA of a cost that can be, let's say, afforded in your application. So once you have these updated constraints, and yes, I forgot to say, you can contact me for a free evaluation account, actually. My email is on there, and you can have a go if you like. Upload your network and see what performance you can get out. So the next step is then, once you have those updated constraints, is to generate a hardware core, a nearBAI core that will be mapped again on your FPGA or on your ASIC, that is really tuned to your requirements, will contain the amount of multipliers of Mac units that is optimum to the application and other parameters. And secondly, with the network compiler, we compile a sequence that will really do the orchestration of all the hardware blocks on that core. This is also important. You can get that hardware IP, as I said, technology independent on the platform of your choice, FPGA, many vendors, the SOMs, and ASIC as well. So there's no silos. We can map to all those platforms. Showcased here using a system on module where you plug in, for example, a trans module or another one, and you can even put an ASIC test chip on the same platform and really rapidly show the performance. Now this is an interesting slide. It gives you an idea of what you can get out of that estimator. So it shows the inference time that you typically want to get low and small. In terms of the number of Mac units, the number of multipliers, typically ranging from a few hundred to a couple of thousand, depending on the size of your chip and the cost, of course. The first graph, what you see is at the left that we are constrained by the number of Mac units, by the number of multiplications. So, meaning if we use a bigger FPGA or put more multipliers on our ASIC, rapidly we see that the inference time is going down, so the performance is getting better, and this can bring us to that optimum. And at some point you see it's not really getting better anymore. That means we are constrained at the right-hand side by the memory bottleneck, basically, and it doesn't make any sense to put a bigger FPGA. So this is really interesting. You can play with that, the same story, like I said, with different lines. The different colors represent not only the width of the memory bus, but also the width of your weights, your coefficients. And clearly, of course, if you make them smaller, it will also get more performant. This is just some examples of how you can tune that engine. I will quickly go over that. This gives you the GUI. This is the tool you can freely evaluate, where you can play with the coefficients. So you can indeed configure the convolution engine, number of multiplier units, for example. You can configure the external memory interface, data rates, data widths, and so on. And then there's also the element buffer memory, which are the internal memories that hold, let's say, local storage of what you read from the external memory. And of course, that also has a play in this mix. This shows the output of the estimator. Layer by layer, you can see what is the time it takes to execute that. And basically, it reports on the critical resources, on the convolution engine, on the post-processing, and also on the internal and the external memory, and shows you really where the bottlenecks are and allow you to play with that, again, to come to the optimum, giving a full visibility.
Some more showing the order of the network, quickly go over. Rapid evaluation board, we are compatible with standard boards by Xilinx, by Intel, also some of the SOM boards like Reflex, CES, and Trends. And then we have, of course, the easics AnySOM board that allows you to interchange these things and quickly, in a matter of days, prototype your application. I see time is up, so let me just finish by this. We can apply it on an ASIC, typically inside of an image sensor, system in a package on a separate die besides the CMOS image sensor die. And we can also apply it in smart cameras, be it starting from a MIPI CSI2 or an LVDS, or from USB, mapping it typically in an FPGA. With very few external components, we don't need a processor. We can put one inside to run your application, and also we can put external RAM for the coefficients and for the microcode. So let me conclude by saying that indeed nearBAI decouples the AI model from the hardware component on which it runs, and that gives, of course, all the benefits that we said. Thank you very much for your attention. And do visit us in this hall where you can see the live demos. Thank you.
Okay, ladies and gentlemen, if you have further questions, don't hesitate to go to the booth of ASICS. We have to stay in time, so here we have no questions. And the Industrial Vision Days will continue with the next session right now, and the next sessions will be about optics and lighting. So thanks again to all the speakers.